Hey everyone! So in this video I'd like to talk more about building expressions. So now that we've learned a little bit about order of operations, we can model more interesting scenarios with expressions. And so let's take a look at a few different examples. So here it says that the oven temperature started at 65 degrees Fahrenheit and is rising 30 degrees per minute. And so we want to write an expression for the oven temperature after t minutes. And so here, the ultimate goal is to write an expression that tells us the temperature of the oven as time goes on for some varying amount of time. And it can be kind of difficult to build these expressions from scratch. And so one strategy we've taken in the past is to, try a few different values for our unknown quantity for the number of minutes that have passed, just to get a sense of what computation we have to follow to get the temperature. And then maybe when we see how the computation looks, we can write an expression that sort of mimics the steps we took. And so here, let's kind of imagine, let's take a moment to just look at the example where t is equal to 3 minutes. Let's look at when t is equal to 3. So I'm not saying that t is always going to be equal to 3, but let's just follow this and see where it goes for a moment, and maybe we can kind of use this to help us build an expression. And so when t is equal to 3, how does the story work? It says that, okay, the temperature it starts at this 65 degrees Fahrenheit, and the temperature rises by 30 degrees Fahrenheit per minute. And so here, if 3 minutes have passed, we can expect 30 degree increase 3 times, right? So here I can write this out as 30 times 3. That'll be how much the temperature increased, but it was already at a temperature of 65 degrees to start with. So that's what we're going to add on, or we're going to add on the 30 times 3 to 65, right? And so this comes out to be 90 plus 65, or 155, right? So here this is saying that after 3 minutes, we got a result of 155 degrees in our oven. Okay, maybe let's do another example just to really make sure we're on the right track. Maybe we can see a little bit of a pattern. So what if, let's say, let's look at when t is equal to 5. Right, so it's the same situation, but now we're just looking at 2 more minutes passed, and so 30 degrees added on another 2 more sets of times. Or you can think of this as we have a 30 degree increase for each of those 5 minutes, right? So here 30 times 5, that'll tell us how much the temperature increased in the 5 minutes, and we're adding that on to what the temperature was to begin with, 65. And so this gives us 150 plus 65. This is 100, no, not 100, this is 215, right? I kind of imagine adding on 50 of the 65 here to get that clean 200, and then I'd have 15 left over to be added on. So that's my result of 215. And of course, again, these aren't the answers to the real question we're trying to ask, but maybe they'll help us get there. And so what computation did we take? Well, we took the number of minutes, in this case it was 5. We multiplied that by 30 so that we can get each of those 30 degree increases for every one of those 5 minutes. And then we added it onto the starting temperature. And so in general, right, if I have 30 times the time that has passed, here t is representing time, not temperature, the number of minutes that have passed, we multiply that by 30 and then add that on to the starting temperature is 65, this produces the temperature of the oven. Maybe I should be more specific, right? The temperature is not always going to be the same as the temperature of the oven after t minutes. Right, so this is our expression. This is actually the result we're looking for. And we can check, right? I can imagine plugging in 0 into this expression. And what would that mean? That would be saying 0 minutes have passed. What is the temperature of the oven, right? So here, if we use this expression, maybe let's just use this expression a little bit just to see that it truly makes sense. If I have 30 times 0, if I'm looking at when t is equal to 0, we have 30 times 0 plus 65. This is equal to 0 plus 65, or in other words, just 65. So here this is saying that the temperature is 65 when the time is 0, and that makes sense, right? That's what we said, is that after 0 minutes have passed, the temperature of the oven is 65 degrees Fahrenheit. So here our expression works even for that. And we can try other examples, yeah, maybe let's do one more just to really illustrate this. I think 0 might be too friendly of an example to really convince anyone that our expression is the right one. What if we tried 10? Right? 30 times 10 plus 65, this would be 300 plus 65. This would give us 365 degrees, and it sounds reasonable. And hopefully when you look at this expression, it makes sense that when you, if 10 minutes have passed, 30 minutes for every single one of those, or 30 degrees Fahrenheit increase for every one of those 10 minutes, would amount to a 300 degree increase, and that would be added on to 65 degrees. So that's just to showcase that our expression makes sense. And really, we've taken this strategy before. A lot of what we've done here is a lot like what we do when we make a table, right? So here in the past we've made tables. Here this would be time in minutes, and here this would be temperature in degrees Fahrenheit. Right, we've made a table many times before, and here we've gone through, I guess now we've found a few different pairs, right? 0, 65, 3, 155. What else happened? We did 5, 215, 10, and 365, and we found a pattern to get from our time to our temperature. Right? This is what we did in the past. Now here, for more complicated expressions, there's not just one operation that's happening to our time input. It's a little bit less easy to see from this table what the pattern should be. And so my recommendation, if you want to build an expression, is to kind of run through this approach and just look at how you would go about computing for concrete examples the result you're looking for. And then you could say this more general result for a general variable value t. One thing I want to mention here is, so I saw in the homework a few times that when people tried to look for patterns in a table, they look for patterns between the different entries in the same column. And there's no real pattern here, right? We kind of just chose 0, 3, 5, and 10 earlier in our computation just to have an example of something to compute with, right? A sort of minute to start with. But there's no relationship between why we chose 3 and why we chose 5 here. So when you're looking at your table, typically you're not really looking for a pattern between the two entries in your column. We're looking really for a pattern to get from the one entry in the left column to the corresponding entry in the right column. So we're looking at how we can get from the left side to the right. So this is the pattern we're trying to find, or the rule we're trying to build to get from one value to the other. And so one other thing I'd like to reiterate is, again, in this example, there were two operations that happened to our input. First there was multiplication, and then there was addition. And so there's, in the past we've only looked at examples where we could get from the left side to the right side through one operation. In this example, we wouldn't have been able to find anything. We wouldn't be able to find a rule here. So just keep in mind now that we're starting to deal with more complex expressions, and that might involve multiple operations in a row. So let's take a look at another example here. It says, Moira canned 80 pints of tomatoes. She kept some of those pints for herself and divided whatever was left over, divided the rest equally among her 4 siblings. And so here it says that if Moira kept m pints, so we have some unknown amount that she's keeping, and then we want to write an expression for the number of pints she gave each sibling. And so again, let's go through the same thought process of, let's try an explicit example first for this value m and see how we might compute what we're really looking for, the number of pints she gave each sibling. And maybe that can give us some intuition on how we can build an expression for this situation. So here, let's look at the case where m is equal to, I guess I chose a starting example of 40. And so here, if m is equal to 40, how would we compute what we're looking for here? M is equal to 40 means that she's keeping 40 pints for herself, and then we're looking for how many pints she gave to each of her different siblings. Well, the story says that the first thing she does, she keeps some for herself. So here we're going to take this 40 and it's going to get subtracted away from the 80 pints that she started with, right? That's she has 80 pints, she's keeping 40, then we're going to take that 40 away, and whatever's left over, that's what she's going to split up evenly amongst her siblings, right? So here I can kind of imagine computing the result for each sibling as first starting with 80, subtracting away this 40, and then what we're going to do is we're going to divide that result by 4, because she's going to evenly split the rest of the pints among her 4 siblings. And so here, I can imagine dividing by 4 next, but order of operations would tell us that first the 40 would get divided by 4, and then we'd subtract that away from 80. And that would be not quite the same as subtracting 40 first and then dividing by 4. So first thing she does is she takes 40 away for herself, and the rest gets split up evenly. And so here, 80 minus 40, this is equal to 40. We still have this division by 4, and this is 10. Right? So there's 40 left over. She splits them evenly across her 4 siblings, and each person gets 10. Right? If we were to do this the other way, and we were to write 80 minus 40 divided by 4, well, we would perform the division first, and this would be 80 minus 40 divided by 4 is 10. So it would be 70. And 70 is not the right amount she gives each sibling because, well, she doesn't even have that much, right? If each sibling got 70, that would be 280 pints of tomatoes. And she didn't have that much to begin with. So here it's very important that we had these parentheses to really express that. First, she's taking some for herself. We're doing the subtraction before the division. Okay. And so here, maybe let's go through one more example kind of quickly. So 80 minus 20. Let's look at the case where we have m is equal to 20. And so if m is equal to 20, she would first take off 20 pints for herself, and then she would divide the rest evenly across her different siblings. And so we would have 60 left over for those siblings. We would divide that by 4, and each sibling would get 15, right? And if you're not so confident with this computation here, I would recommend whenever you see 60, you can kind of think of it in terms of time, right? In an hour. There's 60 minutes in an hour, and if I split that up, well, a quarter of an hour, or 1/4 of an hour, that's 15 minutes. Okay, so here, this is just to illustrate another example of an explicit value for the amount of pints that Moira keeps for herself. But if we look at a general value of m, we would just kind of follow the same approach, right? Here, really, in general, each sibling receives, well, we would take 80, we would subtract away whatever Moira took for herself, and then from that result, subtraction first, we would then divide the rest among her 4 siblings, and this would give us how much each sibling received. So this is the expression we're really looking for. And I definitely encourage you to test different values in this expression and really convince yourself that this is the case, and this is the expression we want. So let's take a look at one more example here. It says that Alicia keeps $100 in cash from her weekly paycheck and deposits 40% of the remainder into her savings account. And so if Alicia's paycheck is represented with this variable P, we want to write an expression for the amount she deposits in her savings account. So let's follow the same approach. Let's pick an explicit value of P and sort of trace what happens with that value of P, in this case, the size of her paycheck. And I think that might be a good idea. I feel like, a problem like this, it's kind of hard to parse all of it right away, and it might be nice to just pick an example and sort of follow what happens to that example to really understand the situation at hand. So here, if we let P what's a reasonable example that might be useful? Where she's taking away $100, she's taking 40%, maybe 300 is a sizable enough example that might work out nicely. So here, let's just kind of trace what happens if P is equal to 300. Maybe this will help us build an expression. We get a sense of what an expression should look like. So here, Alicia keeps $100 in cash from her weekly paycheck, and she deposits 40% of the remainder into her savings account. So 40% of the remainder into her savings account. So this is really telling us that, this is happening second, right? The remainder is telling us that, whatever is left over, she's depositing 40% into her account. So, this is happening second. What's happening first is that Alicia keeps $100 in cash from her weekly paycheck. So the first thing she does is she's going to start with her weekly paycheck, and she's going to pull out $100 from that paycheck, separate that out. And then the next thing she does is she takes 40% of that, whatever's left over after the subtraction, and that's what goes in her savings account. So here, first I'm going to perform the subtraction, and then I'm going to take 40%. And how do we take 40%? Well, here we can multiply by 0.4. You might write 0.40 just to really make it clear that it's 40%. Another thing you can do here is you could also imagine multiplying by 40 out of 100. Right, that's the same as 0.40, as 40 out of 100. Sometimes this is kind of nice. Fractions can be friendlier to work with computationally than decimals sometimes if you don't have a calculator, but let's just stay with 0.4. And so how would this work out? This is 0.4, and then in parentheses, that's what we evaluate first. 300 minus 100, that's 200. And 0.4 times 200, now this might not be as obvious of a thing to compute, but with the calculator we end up getting 80 out of this, and that's saying that $80 is what she puts in her savings account, right? First she separated off 100, and then she took 40% of that result, and that 40%, that's what's going into her savings account. So that's this 80, that's exactly that, the amount that's going into her savings account. Maybe let me just quickly showcase that if we had written this out as 40 out of 100 times 300 minus 100, that this would be something we could evaluate without a calculator. So here, first thing we do is we perform the parentheses, evaluate the parentheses, and we get 200, right? 300 minus 100, that's 200. We still have 40 out of 100. And we can always reduce a fraction like this, where there's no addition or subtraction involved in this fraction in the numerator and denominator. We can just reduce this fraction. This can be rewritten as, I know that they're both divisible by 10, the numerator and denominator, that's 4 over 10. And this is still being multiplied with that 200. And now when we multiply with a fraction like this to some number, well, it's like multiplying the numerator and dividing the denominator. And it doesn't matter which order we do it. Actually, the result will come out the same. And so here I can imagine evaluating this by seeing this as, I can imagine applying this division by 10 first to my 200. And so this gives us 4 times, well, if I divide 200 by 10, that's 20. And then multiplying by 4 gives me 80. Right, so we still get that 80 that we expected, that we saw earlier, that we got with a calculator. But this is a way we could do this without a calculator. Okay, so that's checking one example, and hopefully you can kind of see that, in this example, this 300 was the value of p that we're kind of choosing just to have an explicit example. This 300 is really in place of that variable, that varying quantity p, the unknown value of her paycheck. And so really, in general, if I wanted to write an expression for the amount of money she deposits into her bank account, well, I would just replace that quantity 300 with our variable p. Right, so here I'd write 0.4 times, in parentheses, p minus 100. And this would kind of follow the train of thought that happens in this situation, right? Take away 100 from her paycheck first. She separates that out. Not sure what she does with it, but that's okay. Maybe she buys groceries for her parents or something. But she separates out that $100 first, and then we take 40% of it and we put it inside the savings account. And so that would happen second in this expression. And so it really matches the scenario. This is a nice expression to represent what's described above.